super happy to be here. It's actually some kind of a bit of a different audience that I'm addressing. I didn't found any startup yet, I guess. I'm more like a researcher, really, but in the AI lab of Facebook. And so I will try to explain a bit what we do, but more importantly, that there is a big hype about AI, of course. And so a bit of explaining about why we do AI and what we can and what we can't and what machine can and what machine can't do, this kind of thing. So just the first slide to give an introduction about what Facebook is. It's more about, I guess everybody knows, it's more about like the scale. I mean, it's billions and millions, billions of posts. This is just every day, so these are big numbers for what happens every day. This is massive, and this is also justification why Facebook is actually interested in AI. Is that the mission of Facebook is to connect people together and also to make them basically share what they want. And so if you just take this mission and then you basically put it in the world, you experience that people speak different languages. So you might like to be able to translate automatically. Most people have actually friends speaking another language. So the translation is at the core of what we do. If you want to do good translation, you would like the machine to basically understand what you say. And so you want the machine to understand what you say. Basically, you want the machine to be smart. The same way for images, you're exposed to a lot of data coming from friends, coming from sources. We basically want to show at the top of the feed at least the one that you might like the best. And if you do want to do that, it's a mix of posts, videos, photos. And so we want basically the machine to have some understanding about what's in each post or each picture or video. So basically you have a better ranking and it's actually better aligned with what you want to do. So that's basically in a nutshell the mission. So AI is everywhere at Facebook. And so I will talk about basically two of the things we do. It's like images and text. But actually if you speak images, there are videos right behind. If you speak text, there is speech also. So everything is more or less connected. So let's say this is basically what a machine sees when you show it an image right now. This is basically what it looks like. So you send the image to a machine, and it's going to run like what's called object detector. And so an object detector is trained for like a set of classes, usually 1,000. I mean, this is the standard, like person, car, tree. And basically, if you have a good system, it's not only able to tell you what's in the picture, like there are persons, but it's also going to give you what we call bounding boxes, which is these blocks around where are the objects supposed to be. So this is basically what the machine see. If you're basically at the edge of what's possible, and it's not actually productionized stuff, you have segmentation, much better. So you still have the same kind of view, but now you basically have the contour of the object. So the machine basically see this and can basically have a better way of seeing what's happening. Then you can have actually a better understanding about the classes. So it's not only person, this can actually be man, which means that you could also be woman, and so it's better. And so now, if you want to go deeper, you can actually have the pose, what we call the pose and the key points. So you see that there are these skeletons. And so basically, you don't not only have the shape, you basically start to see that there are arms and the legs. And so you try to basically figure out what are this man doing. And then you have, so you can actually do action detection. So the key pose and the action detection is basically at the edge of what we are doing now in the research. So you can see one of the men is swinging, the other one is crouching, and the last one is watching. So what is this picture about? Baseball, yeah. So there. So basically, if you, so of course, this is what you see. For a machine, this is just pixels, so just numbers. So it doesn't see what you want. But we would be very happy if we're able to basically be there, right? If you can put this into a machine, you were able to tell that it's baseball. We could have a very good, like what we call the semantic of the image in this point. So this is, right now, I would say that the best systems are doing this in production. Most of them are doing this, and some are not even doing the boxes. So it's just like, this whole image would just be persons. Okay, so we have work to do. And so, of course, most of the method that are used now for doing this are neural networks, and most importantly, convolutional neural networks. And what's pretty funny is it's actually not a new method at all. It's actually, so this is a video from my boss, Yann Lequin, 1993. So it was actually, this is a live demo for a TV of actually using like convolutional neural nets to do like unwritten detection. So instead of saying person, you just try to guess what are the numbers. Okay, but this is exactly the same task. This is exactly the same architecture, what's being used right now. Okay, so in 1993, so like more than 20 years ago. So what changed? Well, this changed. So in 1993, we were there. Now we're more or less like, for $1,000, you can have like 10,000 gigaflop. So which is like, you have pretty much of an increase. And this is one of the key of the success of AI right now. It's not like smarter models. It's not like much better brain induced. I mean, whatever key buzzword you have, this is one of the key. You take the model of Jan Leuka in 1983, you put it into these machines, you add much more data than we had at the time as well. This actually makes, and then you have very much better performance. And so this is basically the ImageNet challenge. The ImageNet challenge is the challenge every year to try to rate all the system for doing like image classification. Okay, so you see the rapid increase for like 50% accuracy to like 80% accuracy. This is in 4 years, and this is progressing super fast. And this trend is actually when we started to use GPU. Before there were no GPU. And there is another plot that you can put on this. You like data. So these are actually the size of the models in terms of the number of operations they need to basically run through. This one is pretty massive. Actually, it's not even the best one. So you can be clever. This is very interesting, right? This one is 10 times smaller in terms of size and number of parameters. It's actually as good. But you see there is a trend, and it's still in millions of operations. So it's connected to what we do before. The model that Jan was doing in 1993 was much slower, is much smaller than everything there. And actually, I think not even like 10 years ago, people were not thinking that we would be able to run model this big. And actually, we're doing this, and next year we will run them on mobile. So, wow. yeah, it's pretty insane. So when you have good models, then you can try to say, okay, I show you before that the machine was able to tell there are men crouching and stuff. Okay, but this is not really AI. Let's try to have something smarter. So this was super popular last year or 2 years ago in the research community. Wow, machine can actually describe images. So you show this, and then the machine can say, a man is riding a wave on a surfboard in the water. On the other one, a giraffe is standing on the grass next to a tree. So this is machine learning. You put a curve net, so the kind of model I talked about on the image, and then you have what's called a recurrent neural net to generate the text. You plug them together. The model never saw this image. He's able to describe it. Everybody was super impressed at the time. And actually, this showed like a lot of hope. But actually, it doesn't work all the time. So if you have like more difficult examples. OK, yeah. So basically, I guess the computer didn't want to show this. I don't know. So what I showed before were actually images that are pretty popular with popular objects and popular situation. Basically, when you have someone on the water, it's basically usually surfing, so it's actually pretty easy. I mean, it's not completely trivial, but it's pretty easy. If you go to unusual situations, then basically the model is going to try to put this into usual cases as well. So basically, the one on the left is pretty funny. I mean, if you have a man and you detect, basically what does the model is that it detects object, the way I showed before, and then it tries to fill in the blank by putting some words that appear frequently with this object. And so basically, so basically this one detects a road, and then it detects a plane, and so basically it's a plane. If you have a road, it's not a road in this case, it's an airport and a tarmac, and so what do? You're parked. So that's that. Okay, so there is a bit of a problem there. Okay, so it's crashing all the time now. Okay, well, let's keep it real. So what people try to do now is that to move to caption, what's called caption generation, which was actually super promising, but actually people realized that actually the machine was not that good. To what's called now visual question answering, which is more about trying to ask questions about images. This is much harder, actually, and the task has been very popular for the last 2 years. Actually, it's too hard, which means that there is a big ceiling in terms of people can actually answer a lot of very simple questions, but as long as this one, I think, might be feasible, vegetarian pizza, but it's much harder than what we saw before. You have to detect that there is meat, and meat doesn't meet with vegetarian, so it's much harder. You have to do a bit of reasoning there. If you go on this one, it's even harder. You have to understand that 20/20 vision contradicts the fact that the man has glasses. So basically, now you enter you go from what we call pure vision, try to detect object and try to detect with the best accuracy possible, to basically go into like what is more like reasoning. And so if you go there, actually, you can actually remove the images and try to basically do, okay, can machine do reasoning? And so that's also something we are interested in at Facebook. And so the example I showed before actually a bit hard because we expect that the machine has what's called like world knowledge, knowing that basically vegetarian and meat on a pizza actually contradict themselves, meaning that someone that has perfect vision actually can't wear glasses. This is what's called world knowledge or common sense. It's very hard. So if we want to test that machine can do reasoning, actually at Facebook like 2 years ago, we said, okay, maybe this is already too hard. Let's try to have like very simple situation where we want the machine to be able to do reasoning. So we created very simple stories, like super simple, like this one. Mary went to the bathroom. John moved to the hallway. Mary traveled to the office. Where is Mary? Okay, these are like very simple story. And then you have a lot of different models. You try a lot of AI architectures. You give them the story. You give them the question, and then basically it has to answer. And so you can create a different sets of stories that has different capabilities. We actually created 20 types. And you can go to something that is still small, it's still short stories, but a bit harder. Lily is a swan. Lily is white. Bernard is green. Greg is a swan. What's the color of Greg? Okay. So a little puzzle like this. And then we tested some models. And so basically, when we proposed the task in February 2015, actually most models were difficult. But then actually many people in the AI community pick this task as very interesting because they are very short. Usually you give 1,000 stories for the model to train, and the model has to test on 1,000 other stories that follow the same scheme but with different situations. And you see if your model is able to do that. So it's very easy, no need for very super fast GPU. In this case, you can test a lot of stuff. So last March, actually, we proposed a model that was able to solve 10 of them. Okay, so that was pretty interesting. And then in August, people can solve 2 more. So basically, we are still 3. But now, we are still today. And basically, this one is still unsolved, which is like super easy. And actually, no machine can solve this one. This paper, I mean, this data has been put there like maybe 18 months ago or something like this. It's been cited like 150 times. It's become like super fast, like something very important for testing reasoning in AI system, because it's very easy to use and test like very like simple reasoning situation that we expect a system to have. So of course, to finish, our last part is more about to see, okay, what I just presented was the baby synthetic task. So basically, these synthetic stories where you want to test reasoning on text. But of course, when you're at Facebook, and even if you're interested in actually machine that can do reasoning, you don't want to stay in this simple situation. And people, actually, the critics that we have when we release this, and actually it's a valid point as well, is that, okay, maybe you can solve your 20 tasks. Actually, how does it translate to real data? How are you going to use that on real data? Real data is much more complicated. Everything you show there doesn't work. So this is basically the timeline we're following. We started on the baby synthetic task, and at the end of last year, we also released something that is the same kind of ideas, using like some short stories, but that we use from like children books, real children books. And now we are moved to trying to answer questions directly from Wikipedia. So of course, on this one, if the method is working well, we expect them to work perfectly. On Wikipedia, we don't expect it to work perfectly yet because it's harder. But that's the same idea. And we expect basically the same method to be able to solve all the cases, because we are looking for a method that can do reasoning, whether it's very simple situation or on Wikipedia. So just for the last time I have, just to show you what would it mean to do question answering on Wikipedia in this case. Well, basically, you have this. This is the beginning of the Wikipedia article on the matrix. Okay? And so you can really have your model. So I'm not even displaying any model here. I'm just saying what the model should do. Either it's because it's encoded by someone or because the model discovered that. But the way you would work on doing question answering in Wikipedia is that basically the machine would read the text and extract what are a lot of basically what's called entity or named entities. It can be just done by pre-processing with standard tools, so it can actually be part of the whole reasoning models. But what's interesting is that basically after the reading, when someone asks a question, like what is the source the energy source of the matrix. Then you would like basically the model to be able to read the text, to basically identify what are sort of the entities that actually make sense regarding to the question. Because they are energy sources, because they appear here. I mean, there is a lot of actually components that you want to piece together. And then, in the end, you are able to basically rank all the different entities. So basically, you're just given the text, you create what can be seen like candidate answers, and then you have some kind of reasoning that go from the candidate answer to basically a rank list that will contain basically the answer of the system at the top. And if you do that, you are able to basically work with Wikipedia the same way that you were working on synthetic stories. It works the same, and that's pretty cool. So this last slide is really a work in progress in the sense that nobody can answer on Wikipedia the way that you would answer with a database or anything like this doing reading, but that's really very exciting, and it's not only Facebook work; it's more the whole AI community work. And so last slide on Facebook, because I mean that's where I work from. So to see that basically all I presented is not really Facebook embedded, but we're here on the roadmap. But we have 10 years to go, so that's good. We don't have too much to deliver right now, but it's well, I'm a researcher, right? I said it. So, but yeah, I mean, as I explained at the beginning, and that's why it explained as well, is basically understanding vision, understanding language, reasoning, and planning. I didn't even talk about planning. Actually, a very key element that fits in the whole Facebook strategy for the 10 years. So I can take question now.
This is fantastic. Thank you. So if I understand correctly, the machines are not about to take over the world just yet, right?
We have quite some time before they can even understand the newspapers to realize that they have to take over the world later.
Yeah. So how big is the group at Facebook?
So right now it's like, I would say it's evolved. I mean, we're growing super fast, but I would say we're now 80 people. With like 50 or 60 researchers and the rest of engineers between Menlo Park. So we're not East Coast versus West Coast because we have a part in West Coast, Menlo Park, and one part in New York. And we are even in Europe because we have a part in Paris. There is a French bias there, yeah. But we're happy about that.
Very good. And you guys open source a lot of stuff as well, right? Is that?
Yeah, so yeah, exactly. So basically, most of what I presented here, so the data, the small stories, the algorithm. So we have a very cool algorithm which is called Sharp Mask that can actually do the kind of segmentation I presented at the beginning. That can do the shape of all the objects. The code is open source. The stories are open source. We are open sourcing a lot of things. The lab really works like an academic lab, a university lab, as much as we can. We have a lot of collaboration with university. We give grant to university. We have a lot of students inside. So it's super open, yeah.
Very good. Do we have yes, plenty of questions. Yes.
Thank you very much. It's really interesting. An example that you showed, I know when IBM Watson played Jeopardy, that they trained it by reading a lot of documents and then figuring out how to answer questions. So how does kind of their approach compare with what you guys are able to do? And
yeah, that's a very good question. The Jeopardy achievement was actually super impressive. The way Jeopardy worked is that there has been a lot of work in actually creating a database with the answers, in the sense that the system was not directly reading the text. You have pre-processing, which fits in the animation I showed, because the first step where you actually isolate a lot of the answers could actually be done by human, by manual curators, with a lot of pre-processing. That's what they did with a lot of redundancy coming from multiple sources. What we are aiming here is that basically you're just given the matrix article, no pre-processing whatsoever in terms of no manual curation about this could be answers, and you would like to be able to answer a question just using this source. Which is usually called like machine reading or story understanding. So of course, in the end, right now, a system just based on Wikipedia is much worse than what can be done by Watson using all the databases. But the goal is that eventually, by trying to understand the text directly, you can actually at least equal all the information by Watson is in text, in free text. There has been the question about unstructured data versus structured data before. Yes, here we try to see can the machine try to understand unstructured data directly, because eventually we have much more unstructured data than structured data, and so the process of going from unstructured to structured data is very complex. So if the machine can actually go to unstructured directly, would be pretty handy. But this is research, yeah.
Nick had one right here.
Yeah.
Oh, that was the same question. Okay, fantastic.
Oh, thanks. Hi, I'm interested to know a bit more about the research that you're using here and how you're applying that to virtual reality and augmented reality, especially with Facebook acquisition of Oculus. We can share 360-degree stories, images, data capture, photogrammetry. Can the same math and machine learning applications be applied to stereoscopic images? And if so, are you starting that kind of research in the context of all the larger data sets that are being captured through things like gaze and heat map visualization from things like the wearable devices like Oculus and other headsets?
Yeah, so that's a very good question. Everything I described here, and I didn't describe many models, but most of the models actually are not tied to any applications, and actually the lab is not even tied to any application or any product group. So basically everything we do should be can be applied to any image or any video, whatever the format. In terms of the collaboration with Oculus, so Oculus has its own research lab, Oculus Research, where they do a lot of the VR-related research. But the algorithm I just showed to do that can do like the segmentation is actually used by Oculus when they try to have some experiments where you can show images and they can actually show some extract of it. If you want to manipulate images within the VR, they would actually use. Basically, what we do can be applied to any visual input. So, but we don't do the optimization to make it in 360. But they have the expertise in 360. We have some expertise in like usual images, and actually that's the way it works. So the motivation for our work is not product driven, in the sense that if the roadmap of Oculus is to ship this or that, and if it doesn't align with us, they would have to do it by themselves. Because our mission is more about trying to advance like the core capabilities of what the AI can do. But usually it's aligning pretty well, because when you push the boundary, then you open up like new capabilities for models and for products. So that works out pretty well. But us, we're not tied to basically advancing in either Oculus or WhatsApp or Messenger or whatever.
Concerning the text example, understanding the meaning of a text, we can see that it's a combination between machine learning and natural language processing with extraction of entities. And do you think that the improvement that are going to arrive will come from mainly machine learning because of processing, or is it because of the rules of the natural language processing is going to be improved?
That's a good question. So actually, I don't even see natural language processing and machine learning as two different fields anymore that much. I mean, they are because the community are different, but there is a big community that basically do everything at the same time. A lot of new, very interesting machine learning models have been developed using like natural language problems, but actually they've been used in other conditions, like the recurrent neural networks. At first, they were mostly done for language modeling and natural language processing, but now they've been used to generate like frames in videos or something like this, so they escaped. And on the other hand, I think most of natural language processing now is using machine learning, either as a sub-block or as a whole. Our approach here is basically to try to put as little handcrafted features of rule as possible in the system and try to make it learn as much as it can, because that's also some kind of some constraint that forces us to basically try to innovate in terms of how machine can learn. In terms of developing real application, I think you should really try to balance both, because it's true that in the example I showed, if you have a very good process to basically already isolate all the entities, and if you want basically to use something like this, in your product, yeah, you don't want to force yourself to have a network that has to rediscover something that you can actually extract by yourself using your pipeline. That would be completely an overkill. So yeah, I think when you basically want to have something that works well, you basically have to mix both. But if you, for us, it's more about to try to see, okay, what has been done by another system? Can actually the system discover it? Does it make sense? I'm organizing a workshop like in 2 months at NIPS, the big machine learning conference, and it's called Cognitive Computation. It's actually mixing like rule-based symbolic method with actually machine learning, more statistical method, because it's a very hot topic right now. So we are thinking about what's the good trade-off, and actually it depends on what you want to do.
Let's hear a couple more, whoever you.
Hey, thanks for the great talk. So I guess in one of the examples you had, the model had a severe lack of knowledge or common sense. Where do you see the future of interaction of like neural networks and knowledge? And what are some of the most models that you're most excited about these days?
Okay, so that's so the model. I mean, for the common sense extraction by models. I mean, if you want to start to make a startup around doing that, and if you can solve it, I mean, I think you can like buy Facebook in 5 years or so. I mean, this is like
I will fund it.
No, this is maybe, yeah, this is like the key question everybody's looking trying to basically get machine to basically have common sense and world knowledge, and some actually should you use by robotics because you can actually do some actions in the world, or can you do that directly by looking at videos, or can you do that by reading text and looking videos, and how do you encode it? Do you have a database, or do you put it everything distributed in some neural network weights? How do you test it? How do you know that your machine acquires common sense? I mean, all these questions are like super important. Many people are actually looking into it. There is no clear answer. I would be super happy if I had it. But that's very important. And yeah, that's what's missing. And actually, that's why as well the visual question answering problem that I showed about the pizza and is even too hard right now. They created the data set. And basically, many methods actually saturated at like, I don't know, 55 or 60% accuracy. The simpler or the most complicated were actually in the same ballpark, whereas human can actually go up to 95, because basically all the question will actually require too many common sense to be answered, and so since no method had it, and so the data set was not super helpful in the end. So that's why we actually developed the story, because the story don't need common sense, but you can just test reasoning. Whereas for my favorite architecture right now, I mean, there are like dozens of them like all the time. But I think something that is very nice is all what's called like the neural network with attention. So it's a bit technical, but for people familiar with it, it's very nice. It's basically a model can try to answer, but by answer, it can actually also, the model can decide itself to do like some focus on some part of the input that has been given to it. Some of them are like called memory networks or this kind of thing, and that's nice, because when you do some focus or some snapshot of the input, then you can actually, this snapshot can actually use some kind of symbolic knowledge as well, and so you can try to merge like symbolic and neural approaches there. So I would say that's very exciting.
Yeah, let's do 2 more reasonably quick ones.
Yeah, I'm answering too long.
So,
No, this is great. This is great. No, trust me, this is great.
a lot of AI research in the past has been done with this approach of taking a data set where everything's labeled, and then people apply machine learning to that, and then they're scored on some sort of a benchmark. But that doesn't necessarily scale. So the really important, interesting problems kind of almost need like a human in the loop, but not really a human in the loop to answer questions, but to help label data that's most relevant for the problem. So I'm curious, at Facebook Research, how much are you experimenting with this, hybrid intelligence where, the human is sometimes in the loop and kind of assisting the AI to develop models, to explore data, to pick what data to label?
Yeah. So that's a good question. So I guess the way we call it usually active learning, in the sense that basically the model has to select the example you want to show to a labeler, and the one that should have the most value to be labeled. So I mean, we do like many models, and actually sometimes we will use like Amazon Mechanical Turk to just label a subset of the data, depending, because these are the examples where the model fails all the time, or because they are examples that are from another distribution. I mean, we do that. I mean, the best example is more the M. I mean, Facebook Research, we've been working with M, the assistant of Facebook that is used by a subset of very lucky users. And so M is actually an AI, but supervised by humans. So there we can plug some models, and actually but the system is supposed to have very good accuracy and like very high performances. So basically the system is always monitored by humans, going to decide if what the system decided to do is right or wrong. And if it's wrong, actually going to give what should be done instead. And so that's amazing data set for testing this kind of thing.
So the last question of the night, and then you'll be here so people can ask you questions directly. But then actually the gentleman behind you is the microphone, but by all means, feel free right after this.
Kind of the inverse problem to with a movie script. You might have descriptions of actions and speech. Is there like multimodal learning research going on at Facebook to like take video with audio and extract common features from them?
Yes, there is I mean, I would not say a lot, but there is quite some. And try to so either like try to do remove the video completely and to see if you can actually do like action recognition or trace summary of video, but without actually using the video, just the script, or the other way around, try to generate the script. We have a product. I think it's been shipped in the US at least. It's for description of videos, automatic description of video for blind people. So basically this uses the technology I showed before to basically detect the object. And using that, we can actually generate a description that would say, okay, this picture contains 3 people around the ball, and one is trying to hit it with a bat or something like this. And so I think we can do as good as that, actually. But and so yeah, so that's very important there. And so there, this is a multimodal thing because we have some video that's been labeled. We can also use the speech of what's happening in the video to detect if it's outdoor or indoor. For instance, it's very helpful. And then you detect the object, and so you can generate something.
All right. Well, thank you very much. That's terrific.